Next up, we've got the Ubisense founder and Chief Technology Officer, Andy Ward, and our Global Head of Pre-Sales, John Heathcote. And they're going to share some of the latest developments here at Ubisense, together with some short demonstrations. So I'm joined here by Andy in the studio and John, who's connected remotely. And I'm going to resist the temptation to steal any of their thunder. I'm going to hand over straight to them to take us through their presentation.
Hi everybody. I'd like to take the opportunity to tell you a little bit about what we're doing at Ubisense HQ in Cambridge. I'm going to talk about a new tracking tag that we have just developed, and also a new kind of sensor that allows us to detect angle of arrival and time difference of arrival from all different directions. But I'm going to start with the Ubi tag, which is our smallest, cheapest and lowest power tag ever. It's also our most capable tag ever. It's a multi-mode tracking tag. It's got 3 different modes of operation. It tracks using ultra-wideband technology within the Ubisense system for the most precise positioning in the toughest environments. It also works with our partner Quipper's Bluetooth Low Energy angle of arrival system, which allows us to provide very cost-effective coverage over wide areas. And it also works as a Bluetooth beacon using either iBeacon or Eddystone technology, allowing us to interact with the tag using phones and determine presence information that way. Now, you might think that if it does all of these things, and it can actually do all of them simultaneously, that means that it's a more flexible tag, and you'd be right. So we can take a package, for example, that comes into a factory and attach one of these tags to it. And we can take that into, say, a loading bay. And in the loading bay, we may only want to know roughly where that item is. And in that particular area, we can use Bluetooth Low Energy beacon sensing using a plug-in sensor like that. They're very, very cheap, to find out where that particular parcel is to within perhaps 5 or 10 meters accuracy. And then as that package moves through the facility, maybe it moves into a warehouse where perhaps we need slightly better accuracy, perhaps a meter or 2. And there we can use exactly the same tag, transmitting Quipper signals, and use the Quipper location signal system to find out which particular area of the warehouse it's in. And we can also then use the same tag whilst the package is moved to line side, where there's lots of metal, it's a very challenging environment, and we need to know exactly where that particular item is, with the Ubisense system using our ultra-wideband technology to find very, very precisely where that tag is. So the same tag can be used all the way through the life cycle of a package moving around the facility using different location modalities to get the right balance of performance and cost whilst we're tracking it. We're doing all of these things simultaneously, and you might think that that means that the battery lifetime of the tag would be compromised. Not at all. The Ubi tag is actually our longest lifetime tag for a particular size of battery, and it's actually more than 6 times the battery lifetime of competing UWB tags using similar batteries. So if we look at the battery lifetime of a tag which is transmitting ultra-wideband once a second continuously, so no cheating using accelerometers or anything like that to detect motion, something that's transmitting once a second all the time, then a Ubi tag will last for over 10 years in that mode. A competitive ultra-wideband tag might only last 1.5 years. So there's a big difference in the performance of the battery lifetime. If we look at the Ubi tag in BLE mode, it's over 13 years. And actually, we can do both of those things together, ultra-wideband and BLE, and still get nearly 8 years of battery lifetime out of a tag. So it's a very, very long-lived tag device. Now, because we're expecting these tags to be out in the environment for many, many years, we have to build them tough. And we've built the Ubi tag for industry. It's very compact. So the main body of the tag is about the size of the top of your thumb. It can attach to anything and it's not obtrusive. It's tough. It's a sealed unit, tested to IP69K. Nothing can get in. It will last for a very long time. We've driven cars over it. It has multiple BLE antennas, so it allows those technologies using BLE to work more effectively in tough industrial environments. And it has a magnetic button that allows us to interact with the tag by holding a magnet close to it without actually having to put any kind of break in the case, which might let in water or similar problems. And it can be attached to all sorts of different items in lots of different ways. So we can use tie wraps, we can use screws, we can glue it to things. It even comes in different form factors where we don't have the mounting lugs, we've just got the main body, and as a watch type form factor that allows it to be used for tracking personnel. It's also the lowest total cost of ownership tag that we can see out there. So if we look at an ultra-wideband application where we're using a tag for about 5 years, tracking it twice a second continuously, which might be the kind of level of performance we're looking for in a factory, the UB tag is cheaper than competitive ultra-wideband tags right from the get-go. But because we've got such a long battery lifetime, we also win in terms of the total cost of ownership. For that 5-year battery lifetime, the UB tag has got enough battery lifetime to get us through to the end with the battery that it had on day one. But that competitive tag needs its battery replacing roughly every year. So every year we have to pay for a new battery, and we also have to pay for the cost of going and finding that tag and bringing it back, changing the battery and putting it out there again. Now we've talked to our customers and that cost can be anywhere from $10 to $80 each time a battery change or battery recharge cycle is taken into account. Here I've assumed that it's at the low end of that scale. But by the time we've done that 5 times, you can see that the total cost of ownership of that tag over the 5-year period is more than 3 times the total cost of ownership of the UB tag. And we can do a similar calculation in the BLE space. So although the UB tag is more expensive than competing BLE tags, they're extremely cheap, made in very, very high volumes, but they also have very, very small batteries. So the UB tag probably lasts about 3 times as long as one of those other tags. And again, by the time you've considered taking that tag, bringing it back, changing it for another one, these BLE tags tend to have sealed batteries. By the time you've done that a few times, the total cost of ownership of the UB tag is about half that of the competitive BLE technology. So not only is it our most capable tag, it's also the lowest cost of ownership tag. Looking at the infrastructure side of things, we've introduced a new omnidirectional sensor. So our sensors are quite special in the ultra-wideband world in that we measure both time difference of arrival, the time of arrival of the signal coming from a tag at a sensor, but we also measure 2-axis angle of arrival. So we measure an azimuth and an elevation angle for that incoming signal. And that lets us find the position of a tag using only information from 2 sensors. But our previous sensors were directional, so they tended to be placed on a wall, looking into a space and cover a certain sector of the field of view that they were looking into. Our new omnidirectional sensor can be placed in the ceiling, looking down, and it has an essentially hemispherical field of view, so it makes it much more cost-effective to cover large spaces. I've got an example here. If we take this map and we say, what does it take to cover this with sensors? Well, if we use standard Ubisense sensors and place them in the middle of the space, each one would cover a certain field of view. And we'd have to connect that via cabling to a PoE switch, a power over Ethernet switch in a switch cabinet using Cat5 cable. And obviously, if we want to cover large areas, we have to tile these fields of view so that the whole area is covered. And that involves a lot more cabling, more switches, and so on. But if we do the same thing using Omni sensors, we can do it much more cost effectively. We can do it with fewer sensors, fewer cables, fewer switches, and the total time to value is much reduced. So I'm going to hand over now to my colleague, John Heathcote, who's going to show you some of these new technologies in action.
Thanks for that introduction, Andy. So let's now take a look at how we can put some of those technologies into action and solve some real customer problems with Ubisense's smart space platform.
Let's take a look at a typical manufacturing environment. Here we can see a smart space digital twin of a customer production environment. And in this particular environment, what the customer is interested in is ensuring that the right materials, which are depicted by these blue pallets with stacked goods, are being delivered to the right locations in the material flow process at the right time. This is a really common problem, and many customers that we engage with are looking to move away from traditional manual bookings into their ERP system using things like barcode scanners, because being manual, those processes can be both error-prone and timely. So what we have in Smart Space is this ability to geometrically model the production environment and also build a spatial model that represents all the interesting areas, in this case, of the material flow process. And so, what we can see as material flows from the warehouse to various downstream storage locations, and eventually what we can see over here, these are line-side consumption points. We have smaller and smaller footprints for material to be located, in which and therefore more stringent requirements in order to register material arrival in each of those locations. So this implies an increasing level of location accuracy requirement for materials that are arriving at each of these locations. And this is therefore a great example of what can be achieved with a multimodal tracking system using the UbiTag that Andy's introduced and Ubisense OmniSensors. So in this area here, where we can see we've got fairly small zone requirements, we can achieve wide area coverage across these line feed locations and these nearby storage buffers with Ubisense OmniSensors. And they will allow us to track this material with pinpoint accuracy to guarantee the correct association between those materials and the various control points in the material flow process. So you can actually see an example right here. If I get this pallet over here to move into one of these line feed locations, you can see that this pallet is now being tracked to around 15 centimeters accuracy, and we get a highly reliable spatial trigger as that material arrives into this tightly defined line feed location. If we now zoom out and shift over to the warehouse as another example, what we can see here is pallets are stored in a fairly large area, and the spatial zone that represents the warehouse is much bigger. And by way of comparison, we can see that the required location accuracy to confirm materials inside the warehouse is much lower. In fact, what we can see here is a pallet that's being tracked also with the UbiTag, but in this case, we're using a lower cost angle of arrival based Bluetooth low energy real-time location system with a typical accuracy of about 1.5 meters. And that would be perfectly acceptable for confirming and asserting that materials are located in this warehouse, and also going and finding those materials if needed using a map. So in so doing, we're able to use the best of multimodal sensing capabilities to achieve reliable location data everywhere in the material flow process. So let's now switch over to see how that material flow information can manifest itself inside SmartSpace and be consumed by business users on the shop floor. So here you can see a simple overview dashboard built using SmartSpace of all our material status information. We can see exactly where we have material shortages. In this case, we can see our line feed locations are all lacking material availability. And we can also, using SmartSpace's process logic capabilities, build things like prioritization capabilities that tell the fulfillment team where materials are required the most urgently. We can see in real time where all of our pallets and materials are located, and we can see those movements happening in real time on the map. Let's say I wanted to request that one of these pallets moves down to line feed number 2. I can immediately move that pallet to line feed 2. And we'll see in real time, as that pallet arrived, our line feed 2 material increments, and the amount of material we've got at various locations changes as well. And the priorities for our fulfillment have changed because line feed 2 is no longer lacking materials. Now we can head back to Andy to get some more exciting product updates.
Thanks, John. Now I'd like to talk a little bit about how we go about deploying our systems. The stages in which we deploy are typically split into 4 components. First of all, we'll go and survey a particular site that a customer has invited us on to take a look at. And that's really about understanding site environment and the application that the customer wants us to implement. Once we've done that, then we can start planning the sensor system that supports that application. And that's really got 2 areas. We look at the sensor layout, work out where the sensors might be placed and so on, what fields of view they have, and then check that will provide coverage that's acceptable in terms of application performance and so on. Then we'll go on to install the sensor system, and that involves placing cabling to support those sensors and actually physically installing the sensors themselves. And finally, we'll calibrate the system. That means surveying where the sensors are placed and orientating the sensors and so on, and then checking that the system is working properly and meeting the performance requirements that we originally set out. So our aim in development is to try and improve the time to value here for the customer as much as possible by shortening these areas as much as we can. So if we look at the environment capture area, the survey, the way that this used to be done is that people would come to us with a floor plan for a facility, and we'd try and work out from that where we might place sensors, where in those areas the sensors could see, and so on. The problem was that no floor plan that is in existence for any building is exactly right, and it doesn't really tell you much about how the building's being used. So we get rid of that, and nowadays what we do is we use laser scanner technology. So this is one of our employees carrying a laser scanner in his hand. It's got a sort of backpack-mounted data capture utility, and what that generates is a point cloud, a bit like this one, which shows a kind of indoor 3D picture of exactly where everything is in a factory so that we can understand how the factory is set up. Now, the point cloud by itself isn't tremendously useful, but we have tools that turn that point cloud into a 3D model with walls and equipment and so on. And we can use that model in lots of ways to then improve the subsequent stages of our installation. So we can take that model, for example, and in the next stage, planning the sensor system, work out where the optimal places and the optimal number of sensors are going to be. We can take the model and place virtual sensors inside it and see exactly how they're going to be obstructed by items in the factory, walls, equipment, and so on, and add and remove sensors until we've got exactly the right balance of performance and cost for the particular customer. So if we see, for example, on this heat map, that there's an area that's shadowed by a set of machines, for example, and we need to place another sensor in, then we can do that virtually before anybody has gone to pull cables out and so on. Once we've got an optimal sensor plan, then what we can do is we can work out whether the performance of the sensor system is really going to match the application requirements. We can send virtual tags into the space and use exactly the same algorithms that we'll use in the final sensor system to analyze signals, virtual signals sent from those virtual tags to our virtual sensors, and check to see what the performance of the system is at any point in that space. So here, for example, if you look at the bottom right, you can see that the tag is predicted to be accurate to at least to at most 0.1 meters at that particular point in space. So it's pretty good there, and we're pretty sure that the sensor system is going to work well in that particular place. Now, at that point, we know where the sensors are going to be, and so we can go and pull the cables to those points and install sensors at those places. At that point, we need to do our calibration. Now, the traditional way of doing that was using what's called a laser total station. This is a kind of piece of surveying equipment, and it allows us to find exactly where those sensors are in a facility to within a couple of centimeters accuracy. And we need to do that because if we want to get centimeter level ultra-wideband positioning out at the end of the day, then we need to know where our sensors are to a similar level of accuracy. The problem with these things is that they're quite cumbersome and time-consuming to use. So again, we can get rid of that and go back to our laser scanning technology that we described earlier. We use this LiDAR scanner, but this time we place a Ubisense tag on it. You can see it just above the orange curved top of the laser scanner there. And what we do then is we take a map of we walk around the facility again, and that gives us a trace of exactly where the laser scanner has passed. And at the same time, we're measuring signals from the Ubisense system, and we marry those two pieces of information up. The laser scanner lets us work out exactly where the sensors are, exactly what orientation they're in, and it automatically self-calibrates the system. So this patent-pending technology allows us to calibrate even the most complex location systems in the time it takes to walk around the facility. This here is an example of a calibration that we did at a car assembly line. And it's actually got two traces on there, although it's very hard to see the difference between them. The dark blue trace is the path that the scanner walks around the facility, and the light blue trace is the results that we got from the Ubisense system after it has automatically calibrated itself from that scanner run. And the fact that you can't really see those two traces as distinct means that the accuracy of the system is incredibly high there. In fact, the accuracy of auto-calibration is higher than the manual approach that we used to use. So we've actually been using this over the last couple of months in some of the biggest deployments that we've been doing over that time. And it's really proving benefits. So for example, we've done a large car assembly plant using this technology in the US. And that's important because car plants run pretty much 24/7. You get very, very small breaks in which you can install and calibrate a system. So time to value there is all dependent on being able to get in, install the system, calibrate it, and get out. Similarly, we did a large US bus depot, and the trick there is being able to do that whilst buses are driving around at high speed through the depot doing their normal runs and so on. And again, the ability to be able to do this in just a couple of hours across this huge bus depot really was beneficial for our team in the US and for the customer as well. We've also been using it in the UK. So we've installed a pop-up eye clinic at a shopping centre in London using this technology. And again, time to value is important for these guys because, of course, it's a pop-up clinic. It's meant to be quick and easy to install the system to support what's a potentially temporary installation that has to be installed very, very quickly. And we did the same thing at a national security site in the UK as well. Here, the challenge really was that the people running that site don't want us on site. They don't really want anything to slow down their operations or for anybody to really be interacting with that site at all. So the auto calibration allowed us to get in, do the calibration, and get out as quickly as we possibly could. And of course, the customer is very happy about that. So John is going to show you a few more examples of these tools in action so you can see exactly how they work yourself.
Thanks, Andy. So what I'm going to show you now is a brief introduction to our new Dimension 4 Sensor Planner tool, which is going to make system planning fundamentally easier and more reliable for anyone who's working with the Dimension 4 system. And the first thing you'll see here is that we have automatically generated a three-dimensional model out of a point cloud generated with one of the approved handheld mobile LiDAR devices that Ubisense has been designing around. And what you'll see here in this model is that we've captured an awful lot of the structure of the building that we've walked around with the device. Now, in order to use the auto-generated model that you can see here to perform sensor planning, what we need to do is focus in on the area that we want to do our sensor planning design around. And so what we can do with this model is that we can take, in this case, all the high elevation and roof details off, so we can see inside the building where we want to do or create our sensor plan. So now you can see we've got a full site model where we can do or create a sensor plan and analyze sensor system performance in any of the required tracking areas for the customer. So let's take a look now at what it means to actually build a sensor plan and look at sensor system performance. So let's start by taking a look at this little room area over here. All we need to do with the sensor planner is to decide what type of sensor we want to deploy and drag it into the environment. So if I come up onto the top left over here, where we've got sensor, and drag one of these down into the environment, the system is smart enough, if I drop it near this wall, to know that I'm wanting to snap that sensor to that surface, which represents a wall structural surface in the environment. So if we now want to reorient that sensor to make it point into a different part of the environment, we literally just shift click into the model, and that makes the sensor point at where our mouse is located. Let's go ahead and start dragging a couple more sensors into the environment. So we can see what a more general coverage area looks like with the sensor planner tool. So a couple more onto this corner here. And one last one in our final corner. So what we end up with once we've done that is this blue colored, almost like a heat map that is spread out across the building space. And the blue color and the depth of the blue color gives us this indication of the amount of tracking coverage and confidence in the tracking that we'll get in each of those areas. So a darker or deeper blue color represents a high degree of confidence and reliability in our tracking. And as the color fades off into lighter blue and eventually white, that is a decreasing level of coverage, and white basically means that we've got no sensor coverage in that area. Now, the coverage map that we have is planar, and so we can come over here and actually adjust the height of the coverage map. And then the system recomputes the coverage, taking those new structural characteristics of the model into account. And you can see now the amount of blue that we've got in our coverage map has reduced. So you can see, for example, over here where we are behind a desk, the sensor system at that height wouldn't be able to see, behind the desk through the structure of the occluding desk. So the model takes all of those structural complexities into account when we're working out this coverage map. So the last thing I want to quickly show you is we switch now to a site-wide view, and I bring in a model that I have prepared earlier where I have deployed sensors all over the environment to give you an idea of what a full coverage map looks like. I'm going to apply some default values to all of my sensors that are in this sensor plan. and recalculate the coverage across the site. If we can see we've got lots of sensors across the site now. The system is now computing all that coverage heat map, and as that starts to get filled in, now you can see across an entire facility, and this could be as big a facility as you like. You get this bird's eye view of the quality of your coverage for all the sensors that you have placed into the environment. So that's all from me, and back over to you, Andy.
Thanks, John. Whilst we were watching John's demonstration, a question came in which asked whether we could periodically do that same calibration task in a factory after the system's been installed and has been running for some time. And the answer is absolutely yes, we can. That's a really good idea as part of a periodic maintenance to check that the calibration of the system is still as good as it was on day one, because as we all know, factories are dynamic places, things get bumped all the time. It's really important to make sure that those things happen. Now, we've got lots of health monitoring, as Wolfgang from Daimler mentioned earlier, that tell us about what's happening in a factory, but that kind of periodic health check is not a bad thing to be doing with any large-scale location system. So the last thing I'd like to talk about is outdoor centimetre level positioning. Obviously indoors with technologies like ultra-wideband, we can track extremely precisely. Also obviously we've done an awful lot of work outdoors with technologies like GPS. And of course, everybody understands how GPS works these days. We have a mobile device, some satellites, and we measure some signals from those satellites at the mobile device to find out where it is. In principle, that's extremely accurate, but actually, in practice, the accuracy of something like GPS, standard GPS, is maybe in the 5 to 10 meter range due to signal errors that are introduced by passage through the ionosphere of the Earth. And that limits the applications that we can use GPS technology for outdoors. It's a great technology, it's very, very low infrastructure, but it's just not that accurate for some of the things that we're doing. So we've been interested in how we can do centimetre level positioning outdoors, and a new technology called RTK GPS is something that we think is very interesting. So the way that RTK GPS works is it layers a whole bunch of technologies on top of each other to get fantastic outdoor accuracy. So the first thing it does is it uses what are called carrier phase techniques, where it looks very, very carefully at the incoming signals from GPS satellites to essentially count how many wavelengths of signal there are between the mobile device and the satellites. And that gives us some extra information about where the mobile device is. It also uses what are called differential techniques. So it uses a reference base station that's placed somewhere near to where you're trying to track the objects. Perhaps it's a fixed area of the factory, a particular base station that's placed in the factory somewhere. And what it does is it looks at the same satellites from the same signals from the same satellites passing through the same part of the ionosphere, and it looks at the errors that have been introduced into that reference base station location by the passage through the ionosphere. And we send those observations as corrections to the mobile device, which subtracts them, and then hopefully we get a more accurate measurement of the satellite signals. As it happens, each satellite also transmits multiple different frequencies. There are military frequencies that we can use and so on. And so now in RTK GPS, we use those as well. And then finally, there are lots and lots of different kinds of global navigation satellite out there now. So there's a GLONASS system, which is Russian. There's the Galileo system, which is European, and there's the Beidou system, which is Chinese. And all of these systems transmit signals that we can actually receive at both our base station and our mobile device to figure out exactly where that mobile device is. Now, the difference is really along the lines of, rather than measuring, say, 8 signals at our mobile device, now we're measuring about 60. And that increase in the number of signals that we're measuring, the amount of information that we've got, and the ability to use differential techniques means that we can get incredibly accurate positioning. So the kind of performance that we see is shown here. So these are 2 examples where I took an RTK unit around our parking lot here in Cambridge. I walked around my car and you can see clearly the path as I walk around the open door of my car. And then what I tried to do is I tried to trace the parking lot number that's on the floor. You can see the scale roughly against my hand there, and it's very, very accurate. You might say, why has it got a star at the bottom rather than a 0? And the reason is because we're only getting 1 update per second, and I was moving the tag around that 0 too fast. But all of the points on that star are on the 0. I can really guarantee that it's accurate to about 1 centimetre. This is the kind of thing, though, that we're going to be using it for. So this is an example where we took a car, equipped it with an RTK GPS unit, and drove around our parking lot. And you can see exactly which parking bay we were in at any time. And the amount of infrastructure required to do this was 1 receiver. So this is an entire car parking yard covered using 1 receiver, and with centimetre level accuracy everywhere. So we're taking that technology and combining it with ultra-wideband to allow seamless indoor and outdoor tracking. Indoors, that tag will use traditional ultra-wideband technology from Ubisense, accurate to a few centimetres. Outdoors, it will use RTK GPS techniques and figure out where it is, and then send that information back to the Ubisense Smart Space software, either over a local area or a wide area or a cellular network. Now, there's got to be a downside to this. The downside is simply power. So GPS is quite a power-hungry technology, and therefore when we're using RTK GPS, we have to be powered by a piece of host equipment. So this isn't something that we'll be placing on large numbers of pallets or large numbers of items that are stored in an area. Rather, what we would be doing is tracking things like the forklift used to move those particular items, or perhaps cranes, or perhaps people using smartphones, those kind of things. This technology is already being used by Ubisense in customer trials, and it's going very well. And we see lots and lots of applications for this in the future. So we see, for example, things like forklifts tracking items that are being placed indoors and then taken outdoors and stored in storage yards. That's a perfect example for using RTK GPS. We have a power source. We can even work out the orientation of the forklift by putting 2 of these units on and seeing how they move relative to each other. The same kind of technology can be used in these enormous yards. This is an example of a wind turbine factory in the US. And the same technology allows us to get centimetre level positioning of all of these items, and also their orientation if we can track multiple points on them using either multiple different pickup units or multiple forklifts across an entire space like that using just 1 or 2 base stations. So it's very, very low in terms of infrastructure cost. And we can use the same technology as well for safety of life applications, like trying to make sure that people don't wander during rail maintenance onto live rails. Here, the accuracy really is important. You've got to be able to tell between this rail, which is live, and the one next to it, which is not, and this technology allows you to do that. So at this point, what I'm going to do is hand over to John, who's going to describe another use for this mixed indoor and outdoor centimetre level precision.
Thanks, Andy. So I'm really excited to show you this demonstration. This RTK GPS capability combined with ultra-wideband truly does give a next level capability around indoor and outdoor high accuracy tracking. What you can see in this smart space demonstration here is a large bus depot where we have a high population of buses being tracked indoors and outdoors. And the first thing you'll notice is how cleanly snapped all the buses are to specific bays in the yard and specific lanes inside the bus depot, ready for pullouts on the next shift. And with that high accuracy location that we now have both indoors and outdoors, we can very reliably manage both the buses and our space utilization in the yard. So we can see for every single bus lane exactly which lanes are occupied and how many buses we have in there right now. And we can also see with a very high degree of confidence which bays in the yard are currently occupied and which buses are in those bays right now. The other thing that this model now tells us, being able to track seamlessly indoors and outdoors, is exactly what process areas our buses are in right now. And while we have yard storage for buses, particularly buses requiring maintenance, we also have our indoor lanes ready for next morning pullouts. And we also have various wash, fueling, and maintenance areas. And so SmartSpace gives us a lot of detail about exactly what process and step our buses are in right now in our depot. So we've got an awful lot of valuable underlying data in this SmartSpace digital twin. And like with many other SmartSpace applications, we can deliver that information to end users in custom web user interfaces that not only tell you where your assets are located, but also an awful lot of valuable status information. So here we have a live web map view of our depot, and our buses are color-coded to indicate their current status. In this case, the color of the bus indicates the current maintenance level of the bus and its readiness to be allocated to the next round of pullouts. So if I go and click on any particular bus, I can see a bunch of information pulled from our depot management system that is now easily visualized against the bus in SmartSpace about the status of that bus. And I can see buses requiring maintenance, what's wrong with them right now, and I can click into those buses and get more useful information. What's great about this as well is I can use this web interface for managing data on our buses as well. So let's say I wanted to allocate one of these buses to a particular route. I can now zoom in, find one of my green buses, find one that's available, and as soon as I allocate that to a particular route, the status of that bus will automatically update. SmartSpace automatically changes that bus's appearance so that everybody knows that that bus has been allocated to a route, and I can see what route it's due to go on and when it's due for pullout. The SmartSpace web map gives us many different ways of visualizing our asset information, in this case, the status information of our buses. We can also see down the bottom here, we have a large collection of buses awaiting maintenance. So as can be seen, SmartSpace, and particularly SmartSpace combined with these seamless indoor-outdoor tracking capabilities, gives depot managers the ability to visualize in a highly reliable way exactly where all their buses are and gain a bird's eye view of the status of all buses across the yard at any time. Thanks, and back over to you, Andy.
Thanks, John. Steve, did we have any questions during?
Thanks, Andy. Yeah, we do. We have we've got quite a few, but I'll ask you a quick one. Someone asking about the Omni sensor, about the range of the Omni sensor, as in what sort of ceiling height is appropriate for that product.
So the range is in the sort of 30 to 40 meter distance. The ceiling height that we've used it on typically so far has been up to about 5 meters, but I think it could go quite a bit further than that. But obviously, at some level you start using the range to get from the sensor in the ceiling down to the floor rather than out and covering an area. So, that's something that we'd look at, with a customer regarding their particular site.
Fantastic. Thanks, Andy. It sounds like that's a challenge for the person that's asked the question. We'll find out precisely just how high that ceiling is that we can mount it on. Thanks so much for your questions. A reminder just to submit them into the panel when you get the chance.